Hi, I'm Nadine von Frankenberg, and my dissertation topic is in the field of thermal comfort. Thermal comfort is the satisfaction of the thermal environment, which is especially important because it affects our health and productivity. Regulating temperatures in homes is relatively easy because you can set up everything to your own preferences. In shared spaces, however, like offices, the story is a little bit different. Let's say we have 7 occupants sharing one thermostat. They all have different preferences regarding the temperature. And this is what we define as a conflict, a disagreement about the temperature between occupants and the environment. This conflict cannot be solved easily so that everybody is comfortable. Therefore, many building management systems use models to regulate the temperature. Many of these models are based on data-driven approaches, such as the PMV or machine learning models. However, they do require large data sets and continuous occupant feedback, which is hard to obtain in practice. In addition, occupants also need to understand decisions why the temperature has or also hasn't changed. For instance, imagine you've just voted for a warmer temperature, but instead the temperature was lowered. And in general, these existing systems tend to bypass conflict resolution through rule-based behavior. This leads to my main research question. How can we resolve thermal comfort conflicts in shared spaces in a fair manner? First, we identify conflicts based on event processing. Next, we need to identify the factors that might contribute to the conflict, such as somebody is sitting next to a window where the sun is shining through, the window is open, or somebody is sitting next to a fan, and take those into considerations when making and justifying a decision. As these decisions are made to increase the thermal comfort of occupants, they need to be kept in the loop as well. And rationale management allows us to include all of these factors. These abstractions are then separated into 3 levels. First, during event processing, the events are categorized to filter out events that lead to potential conflicts. For instance, if an occupant votes for a warmer temperature or a cooler temperature. If a conflict is found, the context indicators, such as who's involved, what's their schedule, because we might not want to include somebody's vote who's leaving in 5 minutes, or what are the current environmental conditions, are identified. And in the 3rd level, the conflict is described using a rationale model that includes the proposed decision, alternative decisions, and arguments. This decision is evaluated based on suitable solution strategies like bidding or different prioritizations or other policies. And at the end, the occupant can review the decision and give feedback in a retrospective. We implemented this as the TREATI framework, which is an open IoT architecture. And TREATI uses the multi-abstraction process that I mentioned before that focuses on rationale management efforts to resolve thermal comfort conflicts in shared spaces. In my dissertation, I follow a mixed methods research approach that focuses on the validation and verification of TREATI. Therefore, we first implemented each level in different projects, and the main goal here was to show the validity of each abstraction level and to find shortcomings in the process. We further evaluated each level separately as well. In addition, we conducted a survey that showed the necessity for different levels of abstraction and occupant involvement in the decision-making process. We further asked questions to understand occupants' self-perceived behavior in conflicts and the kind of control behavior that they would expect. The main goal is to test and evaluate TREATI. However, in the real world, this would require many resources and take a long time, while also putting occupants at risk when testing extreme situations like constantly lowering the temperature or increasing the temperature. Thus, we use a simulation study to verify TREATI against its simulation model and also to validate it against the real world. So far, we've conducted a simplified simulation, which has shown a few inconsistencies that we then, in an iterative and incremental approach, rectified in a second iteration. And next steps are to conduct a more detailed simulation, finish the dissertation, and of course also conduct a human subject experiment as soon as the COVID-19 situation allows it. To learn more about my evaluation and results, please do join me in my poster session. Thank you for listening.